And happy Sunday. This is PFG Live, the podcast that asks you if aluminum is magnetic, what about water? We'll find out later today. Welcome aboard from Windham, New Hampshire. I'm Spencer Webb, sitting in Kinetic Precision. And we've got a bunch of cool people in the Discord and in the YouTube chat. Right here today, by the way, it is 49 degrees Fahrenheit, 46% relative humidity. Tucker is checking in from Buffalo, New York with cloudy and 55 degrees. Evils is checking in from the Belgium, 19.9 degrees science, 11.2 degrees science, dew point, and other things. Dale is checking in from Snow, Mexico with 0 degrees science, clear skies, no wind. Lovely. Mashed Cutting Diamond, who can only be one person, is checking in from somewhere in Ohio, 62 and sunny. Josh is here in South Manitoba, I should say southern Manitoba, where the winds are, let's see, 031 at, no, I'm sorry. Where's your winds? There they are. 160, 11, gusting 17, windy. Temperature 09, dew point 08. And the peak wind was 150 at 17. Pretty windy. CJ Stevens, who opened our YouTube chat. Welcome aboard, sir. Thank you for your feedback. Carl Tauber. CJ says it's 72 degrees Fahrenheit and sunny in East Tennessee. Loading in the car for a Sunday drive to Bristol. Very nice. Carl Tauber is here from the People's Republic of Rhode Island, where it is 50 degrees Fahrenheit and sunny. Hi, Carl. New York Machinist, welcome aboard, sir, where it is cloudy and 50 degrees Fahrenheit from Ithaca, New York. Don't fall in the gorge. Domestic G says it's 59 in Ann Arbor, Michigan. Please say hello to the former home of Heathkit. Welcome. So, I think we caught everybody so far. We had a good week. Sometimes stuff happens and you have to address the stuff. You don't have time to not address the stuff. So that was this week. I'm still trying to get this 2 projects hanging over my head, trying to get them out the door, and we're getting mighty close. And I appreciate my extremely patient clients. In the Discord today, we have Lance K, Tucker, Evils, Mashed Cutting Diamond, I think that's what it is, Quentin, Josh, Dale, Carl Tauber, and Jeff Williams. Welcome aboard. It is gorgeous here today. And I have to give you a hot weather warning for the Northeast because I covered up our air conditioning units. I blew out our irrigation, and of course, turned off the air conditioning. So therefore, it should break 80 degrees this week. We'll keep you posted. I have to give you a warning. We did a whole bunch of testing on YouTube with our software, OBS, this past week. And as usual, Webb's law of engineering problems is it's never one problem. It's always multiple problems. So I finally beat on OBS enough to the point where I think I have all the settings optimal. Now, OBS stands for Open Broadcaster Software. And here's their stream connection troubleshooting. And I went through their entire list, and I think we're doing okay. However, the second problem is YouTube. YouTube is acting very funny. Now, there's a couple things going on. Today is the New York City Marathon, so everybody is streaming to YouTube. That's a possibility. Plus, somebody told me that there's some national event coming up that might impact how YouTube is behaving. I'm actually not really sure what they're talking about. But for those reasons, if the YouTube side of things goes a little wonky, we understand. Because of that, we've selected a longer latency in the YouTube. So if you make a YouTube comment, right now it's only running about 25 seconds. but there will be some latency before I see it. So Carl says, he says, you need to deploy the snowometer to ensure a heat wave. If I did that, I think that would be the trifecta. Blow out the irrigation system, turn off the air conditioners, and put out the snowometer. It might break 90 if I did that. I'm a little concerned. I don't think we want to do that. That's a little too much. But we could expect some pretty weird weather. The trees have dumped. We should have the dumpometer. The oak trees in back are probably 80% dumped. I don't think it's much more than that. Maybe you could make the argument for 85% leaves have been dumped, but we'll see. We'll see what happens. Let's see. One of our esteemed members of our community who checked in earlier, but I think he has some family stuff going on, is Unix Carbide. And we joke about magnets and magnetism and stuff. And one day I said to Unix, I said, well, we use the magnetic aluminum. He was kind of like, what? And so ever since then, I've been ribbing him about things being magnetic, and so the weird thing is that the reason it's a topic today is that it's weird. It's really weird. And once you get past the venerable refrigerator magnet, things get pretty crazy. That was exacerbated by listening to my friend John Saunders, who was looking for a small mechanically operated magnetic chuck for a fixturing project, which I thought was a great idea. And I heard some things in that discussion, which also led me to think about magnets and the need to talk about them and that they're kind of a little weird. So we're going to get into that today a little bit. That should be fun. So I posted, while we're talking about magnetic aluminum, I posted to Instagram, and many of you may have seen that particular posting, that there was a particular container that I liked. It was a twist top aluminum container. And my point was that we use all of these plastic bottles, and the value of the contents compared to the value of the bottle, coupled with the recyclability of the bottle, doesn't make me happy at all. It was like over packaging and poor consideration for the environment, and that's been going on for a while. And you probably, I don't have one here handy, but you probably see me with a plastic water bottle frequently. But we use those. I mean, I must reuse those plastic water bottles literally 200 times before they give up the ghost. So I'm a little concerned about that sort of stuff. And then you see pictures and videos and information on the socials about these ocean-going vessels that are specializing in scooping up all the junk we're dumping into the ocean. So I like metal. This is going to sound interesting because of the rest of our topics today, but I like metal and I like glass because both of them are very recyclable, and they're very effective as containers. So we were talking about the aluminum containers, and a lot of people, pressed like on that post on Instagram. So that goes into the rearview mirror, and I forget about it. All of a sudden, I get, how you get notifications from UPS that you have something coming in the mail. And I have a package coming from one of my favorite tooling suppliers, Mary Tool. Now, if you have a CNC machine and you buy tool holders, you probably have heard me talk about the tool holders that I buy from Mary Tool. I love them. They're great. We have pretty simple requirements. We don't do dual contact. I don't do through the spindle cooling. So they're pretty simple. And I love the Mary Tool products. So they're also a customer, by the way. They have PFG Stones. So I have this package incoming from Maritool. There's only one problem. I cannot for the life of me remember ordering anything from Maritool in the last, couple of months. I'm very well stocked. So I had to wait until it showed up. I didn't know what was happening. And I was really worried that they had another customer's order, kind of, errant mouse click onto my account. So the other day, the box finally comes in from Maritool, and I open it up and I started laughing. So, I do the same thing. I like to ship extra goodies to my customers, and it's a little Maritool pad and a little note, probably from Frank, who said, "I heard you like aluminum." So he said, "I heard you like aluminum," with a smiley face. And I reach into the box, and there are 6 of these. So if you're on the audio podcast, I am holding a sealed, filled bottle of Maritool water, which I am going to guess, I don't think I see any markings on here to that effect, but I'm going to guess that they had these made for their booth at IMTS, and I'm now the proud owner of a 6-pack of Maritool water, and the label says, "Sometimes it's okay to drink the coolant," because Maritool coolant is 100% pure spring water. Keep your cool when things get hot. I love you guys. You're awesome. So anyway, this is what I had coming from Maritool. Thank you guys. I sure appreciate it. And the other thing I like on here is they have a drawing of their tool holder. It looks like it's an ER collet holder. It's super nice. I appreciate it. So I'll be drinking one today. I'll save that. I have to finish my tea first. But Maritool, I appreciate you guys. You have to make your own fun. So that was one thing that happened this week. That was pretty cool. Let's see. We talked about that. So let's give you guys an update on our data from our dry storage experiment. The spoiler is that the ranking of the containers has not changed. So there were no super surprises in the last week, but I think it's important to go over the data. So let's go over the whiteboard here, and I will tell you a little bit more about what's going on. So we'll go in order of ranking, placing last in our rankings, unsurprisingly, is our control group, which is our 2 packages of desiccant. They have become saturated, and actually between last week or 10 days ago and today, the weight of the control units actually dropped. So I looked over, and sure enough, the relative humidity in the basement has dropped from about 66% when we started this experiment to about 45%. So those desiccants are well and thoroughly saturated, and they actually started drying out again because the environmental humidity started going down, which I thought was pretty cool. So that's number 7. The uncorrected percentage per day gain was 2.9 milli%. You guys can go figure that out in weight. Number 6, coming in at the number 6 rank, is the 5-gallon metal pail with lid. Talk about surprising and unexpected, but the 5-gallon metal pail with the lid, with the seal, with the band that's supposed to hold waste products that are dangerous, is coming in the worst of all the containers. So if you look at the data, it it's gaining a pretty steady 0.14 grams per day, and we're unimpressed. Sorry. It's not too good. Beating, and this is not saying much, but beating that is the Sterilite container, the one that I had adopted a while back, in the number 5 position. And that's picking up 0.286 millipercent per day by weight. Better than the Sterilite container is coming in at number 4 is Doug's 4-liter container with foil tape. So Doug found a really nice foil 4-liter container, left one of them as is, wrapped the other one with aluminum foil tape, like HVAC tape, and we fully expected that the diffusion through the plastic was going to be greatly reduced. But in fact, the foil-covered container is worse than the not foil-covered container, and that's coming in at number 4 with 0.109 millipercent per day. And then there's Doug's uncovered 4-liter coming in at number 3 at 0.09 millipercent per day. Yeah, Evils, the units I picked were just to bug you. They have no other purpose. Don't worry about it. The data is available if you want to rework it. That was number 3. Coming in at number 2 is the 30 caliber ammo can. So this is your bog standard shoebox sized ammo can, and it does really well, like amazingly well. Unfortunately, the size of those cans is smaller than a roll of filament. So from the filament storage point of view, not so great. But as a good container, it's fantastic. In fact, it's the best of the metal, lidded containers that we have, coming in at 0.051. And finally, and unsurprisingly, the number 1 performer is our 2.5 gallon Mylar aluminized Mylar bag that is coming in at 0.04 millipercent per day. So the total weight gained, total change in weight over the entire experiment, which has been 30 days, is 0.4 grams for the 2.5 gallon Mylar bag, which, by the way, I have right here. Now, the link that I think I said this last time, the link that I posted to the pfg.gg/links page is now pointing at a different size because they ran out of that size for that brand, etc. But I'll update that soon. The important thing is that these are 7 mil walls. It's Mylar, and it's aluminized Mylar, and it's got a good quality zipper on top. As I was refilling my tea, as you know, I drink a lot of tea. As I was refilling my tea, I noted that my tea comes in these bags. Okay, this should look familiar. And so I started looking closely at the bags that my tea come in. And they, of course, are heat sealed. And they, of course, you have to rip the top off, revealing a zipper lock closure. But the thing that I found interesting was that the Mylar, while pretty, it's Mylar aluminum, and eventually you get to the outer surface, which is kind of a paper. But the amount of aluminizing, the thickness of the aluminum in the stack up, is sufficiently thin that you can see through it. So it's a very, very light coating of aluminum. And apparently this food distributor thinks it's enough. And I can't argue, because I've been buying my tea in these pouches for a very long time. So that's just another example of it being used. My friend Doug will point out, if he was here, he would point out vociferously that Doritos, and Tostitos and various other potato chips come in foil covered plastic bags, and they've been doing that for years. So that's another existence proof of that stack up being useful and a good place to land and cheap. So once again, we'd like more of that, please. So ditch your Sterilite containers, guys. I apologize, but these aluminized Mylar bags are pretty stinking good. Paul Morley has arrived in the Discord server. Welcome aboard, sir. What else is going on here? Greg says they are where to get all the Mylar packaging. You're talking about Amazon? I've been getting stuff off of Amazon. And there are a couple of brands, and of course they're imported. And if you look around, and it has 7 mil walls, and a nice fold out bottom. I don't know what they call that bottom, but they're going to be very, very similar, if not exactly the same. Foil covered or aluminized? I think the answer is aluminized. I think the material is aluminized. Greg says Sorbent, Sorbent, is the leading U.S. manufacturer of Mylar bags and roll stock. Thank you. So I wonder if we can get bags from them. Can I put you on that, Greg? It would be really cool if we could, and it would be even cooler if McMaster Carr can carry them. Then we'd have our favorite catalog carrying our favorite bags, and keeping our favorite filament dry. Thanks, Greg. That's awesome. Fantastic. Well, see, the community solves the problems. That's the bottom line, and we appreciate you. Thanks. Quick question for our YouTube guys: how's the stream looking? Is it looking good? Greg says Sorbent has every variety imaginable. Because YouTube is yelling at me here occasionally that we're not pushing out enough data. By the way, for the nerds, I have enabled 100 megabits per second going out. It's not using it all, but it's available if it wants it. And YouTube's still yelling at me. So YouTube's having issues. So give me a little art that makes art. Wes, hey, he says it's great. Is the stream great, or are the every imaginable variety of bags great? It could be both. ¿Por qué no los dos? Anyway, moving on. So that's the update on data and our ongoing experiment. We're going to keep going until we get one of our containers halfway to saturation, and then we're going to call it, because then the errors will start building up, and we won't want to do that. So that's the update. Now, another member of our community, and Lance, I'm starting to talk about you. Another member of our community. Oh, look who showed up. Test Room 2003 says, good evening. Late at checking in. It's okay. Don't worry about it. From Oostkapelle, Netherlands, 6 degrees science and 100% relative humidity. That's starting to sound a lot like cold and wet. Welcome aboard, sir. So Lance pings me and says, hey, I want to send you something, which I always worry about when I hear that. It could be good. It could be career ending. I don't know. So I sent Lance he told me the weight and the size, and I sent him a label for shipping. And I get this cool little box. Where's the box? Here it is. I get this cool little box in. Okay. And not only was this box cool, it won the packaging award for the month. It was magnificently packaged. I don't think there was extra air in there. And he sent me, if you saw the if you saw the thumbnail for today, he sent me this glorious EDM'd puzzle. I guess we're going to call it a puzzle. And it is just absolutely fantastic. And of course, the K fits in the P. Okay, that sounded wrong. The K fits in the P. I guess K could be potassium. So there's you can make the argument that there's like potassium in the P. And you don't know how cool this is and what kind of a fit it is until you handle it, and it is just amazing. I did post a little video showing the K sinking into the P with just letting air molecules go by one at a time. So let's bring in Lance, and we could talk a little bit about this whole technology of electrical discharge machining, or EDM, in this case, wire EDM. Lance, are you with us? No, he's not, because I have to push this button. Let's try it again. Hey, Lance, are you with us?
Yes, I am.
Oh, there you are. How are you? Thanks for being here.
I'm doing well.
I want to say thanks
for
again.
having me.
Yeah, thanks for the magnificent gift. That it's really cool and very educational. So thanks again. So let's talk a little bit about EDM and how you came to learn and start executing some pretty cool EDM projects.
Yeah, so EDM is electrical discharge machining, and in particular, this part was made with wire EDM, which is one subset of EDM.
Yep. I'm showing the, you had a name for the outside part.
That is the stock material. Could possibly consider calling that the slug, although usually we'd call the slugs the pieces of material that we discard from inside of a part.
And in this case, this outer part was made out of one type of material, which I guess you said was...
It was a 4140 is a piece of pre-ground stock we had on the shelf that I grabbed.
Yep.
Not necessarily a great selection for a EDM part because it will rust, as is visually apparent. But we have some grinding and post-processing that makes things look nice.
Yeah, so after grinding and post-processing, of course, it looks absolutely glorious. I did notice that there's a very tiny color difference between the 4140 and the center section. So what is the center section made out of?
The center section is a chunk of hardened high-speed steel that was also sitting around.
My favorite alloy, by the way, is the one sitting around. So I'm in violent agreement. And how long did it take to cut out? We'll just make believe you only did it once. How long would it have taken to cut these out?
I think it was about 6 hours in total for the machining operations across the 3 sections.
That's pretty cool. 6 hours. But of course, you get points because you were practicing. You were exercising your skills on the machine. What size? So why don't you give a verbal description of the EDM process, and then I have some questions.
Gotcha. So in general, you have a workpiece that you want to cut, and you have an electrode. In this case, it is a brass wire. You bring the brass wire close to the workpiece, and there's an electrical difference between the two, and that causes a spark to jump between the parts, and that removes a little bit of material. The spark lasts for a few microseconds if you're doing a main cut, and delivers something, I think, a few hundred volts and possibly up to maybe a few hundred amps as well in that very short period of time for one pulse. And then that cycle is repeated, many times per second as the wire advances into your part.
And it's submerged in a dielectric fluid, right?
Yes. In this case, it was submerged in deionized water, but there are other fluids available.
But were you using Maritool deionized water? Was that the...
I don't know if you'd want to drink the deionized water.
So it sounds pretty simple. Wire, voltage, water. Years ago, I heard the story of the invention of EDM. And as the story went, it was invented by two Russian scientists who were attempting to figure out ways to prevent high voltage contacts from sparking and eroding their contacts. So they submerged it under, water to see if the dielectric fluid would stop it, and it made it much, much worse. And to their credit, they said, "Hey, this could be useful." And
Yep.
that was one of the. And it turns out now I went back and I read the history, and in fact, those two Russians are named in the history, but also in parallel in the United States was three guys, I think, that started discovering the same thing at the same time, which is pretty slick. So you have wire EDM, which is now, how much wire do you go through? Like how many feet of wire do you think you went through on this project?
So that'd probably be about 6 pounds of 6 pounds of wire. It's about 1 pound per hour, roughly. It can go up or down depending on what you're doing.
So, and that was 10 thousandths wire, right?
Yes, 10 thousandths diameter wire.
So that's a long piece of wire.
It is. It comes on a 40-pound spool.
Wow, pretty neat. Is it straight? You said it was it brass wire? Is that what you said?
It is a zinc-plated brass wire.
Zinc-plated brass. So you can't yank on it too much because brass is not that strong. So I assume the machine has some very good controls over the tension in the wire.
Yes, so the wire goes through a number of pulleys. The pulleys are insulated, of course, and you have to maintain tension on the wire to keep it cutting straight, but you also can't put too much tension on the wire because as the wire is passing through the workpiece and being eroded, the wire becomes weaker.
Okay.
So you've got, two capstans with a rope going through them, and there's a guy in the middle with a wood rasp going at it, and you got to try and not let him win.
So are the parameters pretty well documented? So you dial in this speed, this tension, and then go to town, or is there some tuning involved?
There is a lot of tuning that's involved, and it's all contained within the machine in a database. So
okay.
As an operator, you're typically going to be looking for the process in terms of, looking at what material you're trying to cut and how tall is it. And the machine will give you a number of solutions for your wire tension, your wire speed, how much amperage or power it's going to be putting into the wire, and other variables that it has under the hood. It'll on the wire machines that I run, which are AGI machines, it will tell you what the expected surface finish is and how many passes it will take to get there.
Pretty cool.
There's a whole bunch of math and active controls that are going on inside the computer, but the operator selection part of that doesn't necessarily need to know all the variables perfectly. The software controls a lot of it.
So that's pretty cool. That control is a lot smarter than a typical CNC control, which is just saying, give me G code. That's pretty impressive. So what resolution do you tell it the type of steel that it's cutting? Do you give it alloy, or do you give it hardness, or do you just say steel?
In this case, you'd usually just say steel. It's more concerned with type of material than specific alloy. Mm-hmm. So there's a difference between carbide, aluminum, and steel, but there's not a huge difference between stainless or normal steel in terms of the process on those machines.
And I assume there's the operator can make some observations and then make little fine tuning adjustments.
Yeah, so the machine is constantly reading a closed loop control algorithm to keep the machine in a stable cutting condition. The operator can go in and make adjustments, but it can be difficult to know what adjustments to make because there are a lot of variables to tweak.
So in YouTube, VKTD, welcome aboard, sir, says the machine monitors every single spark that occurs. That's pretty cool.
Yes, on some machines, they will output a data file that can contain the discharge information for every spark to make sure that nothing went awry during the process.
Wow. That's amazing. So did anything go awry during your process?
A little bit. The the start holes that I chose were a little bit too small, so I had some trouble with threading. I
Okay.
used the chunk of electrode that was on our hole drilling machine first, and that was a little bit too small.
So
The
let's expand on that for just a second, if my
Yep.
camera will focus. So these starting holes are separately drilled on another machine. Is that
Yeah,
correct?
we have a small hole EDM drill,
Okay.
which also uses electrical discharge machining in a similar sort of process with a small spitting brass tube, like the one you have there,
Yeah.
and it flushes water through it and moves downwards to drill a
Ah,
starting hole.
I didn't realize it was a tube. I thought that was solid, but those brass parts are tubes. That's pretty cool. So you go over to machine A, you pop the holes in, and then
Yep.
you've got to get oriented over that hole for the machine to spit wire into it. How do you do that?
So the machines, the wire machines I work on have an automatic threading feature, which uses a jet of water.
Oh, neat.
And it's nice because you don't have to thread the wire yourself on all the holes.
Okay.
For the setup process, you would load the part in the machine and indicate it level, and then you can jog the machine over and turn the threading jet on, and it will shoot through, or it'll shoot the water down. And then you can just position that stream of water over your start hole. Is one way of picking up location.
So adjusting the stream is a manual thing, and once you see, oh, I'm it's going down the hole, then you hit the button.
Yeah, you would then tell the machine to thread and pick up inside of that hole. It'll do a touch-off routine with the wire as a probe.
That is so cool. And then once the wire gets threaded, I assume the machine turns on the green light and says, "Hey, I got the wire," and that starts
Yep.
your 6 hours.
Yeah. So there's a little bit more of the details. Having your setup dialed in correctly is very important on the wire, or more so than a milling machine. You can't just set your part in the vise and go. You have to make sure that your part is aligned correctly when you're working with very tight tolerances. The touch-off procedure is important, and you also have to set the height of your upper wire head to get it close to the part, but not so close that you run into anything as the machine is moving around.
You use the word "ped" that I didn't recognize.
Oh, I might have there. Sorry. The upper pickup head of the machine, or
Ah,
the upper
okay,
wire head.
got it. Okay, pretty neat. Um, and then you go away for 6 hours. So are these machines?
You hope to.
You, I was just going to ask you about that. So my question is, what's the relative reliability of these processes? Is it? I mean, I have processes on the grinder that I know I could set up, hit the button, walk away, and come back in an hour, and everything's fine. I assume you gradually get to that level of confidence with this machine. Does it have a reputation of being super finicky, or actually pretty much the same as dialing in a milling machine process or a grinding process?
The particular wires that I work on are a bit finicky. If you have a cycle that needs to go over the weekend, it oftentimes won't. Either you'll run out of wire because you didn't know how much was on the spool, or it may fail to thread a hole, and then the machine will stop and wait, and it's unattended until it needs attention.
Can you have multiple start holes in the same part, and then the machine will finish one process and then go over and thread the next one?
Yes, it will automatically move through individual cuts in a part and complete them. and then thread in the next part or next hole.
That is pretty cool. So the other fascinating thing is that this, in the wonderful puzzle you made for me, the P part is a relatively unhardened steel, right? That's a 4140. And the K is a hardened tool steel. And the machine doesn't care. It's perfectly happy cutting either.
It's you could argue that it's happier cutting the hardened steel, because you can get better surface finishes in a hardened material than you can in unhardened or weak materials.
Which sounds familiar from the grinding process.
Yep.
Here's one of the... So, okay, this is very interesting. So here's, on video, I'm showing two of the little Ks. This is the... Oops, sorry. This is the slug that was cut out of the part, and then this is one of the Ks that is made out of the... Come on, there we go. Is made out of the high-speed steel. And you can see that there's two very different finishes on these. The hardened tool steel came out rather magnificently, and there's this, pretty classic brown finish on the waste slug that came out of the K. It's pretty neat.
So that difference is in the number of passes cut on the parts.
Okay.
The slug, of course, is the first cut, so that is just the wire trying to get through the material as fast as it can.
Mm-hmm.
And afterwards, it will go back through the contour again and recut at a finer power setting to produce a finer surface finish. And that's the difference you're seeing there.
That is too cool. VKTD asks, how many passes did you use for these parts?
I used 3 passes on the internal contour and the external contour of the punch in the die.
Okay. And you used a term I don't think we used yet. So
yep.
Traditionally, you're calling the inside widget the punch, and the outside widget is the die.
Yep.
Okay. And then Tobbs, who reminds us it's just Tobbs, running lights out on a Sunday, came in on Monday just to find out the machine, Mitsubishi in his case, not being able to automatically thread. Well, you got the first part of the project done, right? And say again the brand of machines that you're using?
The machines that I run at work are Agi machines. They're a Classic 2 and Classic 3.
Could you spell Agi?
AGIE.
Excellent. If you guys have any questions, now's the time. While we have an EDM expert here, is it true that in order to be an expert at EDM, you also have to like electronic dance music?
That is the type of music that is played in the wire room, although it's not my choice of music.
Excellent. I expected that. I expected no less. Are there any materials that you've cut that were particularly surprising, either in, oh my gosh, I didn't think that was going to work at all, or I didn't expect it to work and it was harder than anything I've ever cut before in my life and there was no other way to cut it?
A lot of that can depend on previous operations on EDM parts. If a process has to come from milling and then move over to the wire, if the mill guy didn't communicate with the wire guy on what's needed on the parts, you can end up with difficult situations where start holes may not be in the right place, or there might not be enough material left to drop a solid slug out of your part. As far as materials themselves, aluminum it's not difficult to cut in the wire, but you do not get a good finish on it. It's difficult to get to like a 32 finish on aluminum. It takes a lot longer than in other materials.
Do you see aluminum coming in for EDM? I mean, is that a typical
we
thing?
do.
That's interesting.
At my job, we do. Yeah, sometimes. A lot of it is stainless steels or titanium.
Yeah.
But it depends on what the customer wants.
So again, we're going back to the overall architecture of this process. That's wire EDM. It's very analogous to a bandsaw, right? It's the world's most accurate bandsaw. But you also have plunge cutting with I forget the term for it in EDM. What do you call it?
Bisecting?
Say again.
Oh, are you talking about sinker EDM?
Sinker EDM. So are you doing those also?
There is a couple sinker machines at my workplace, but I have not worked with them much, so I couldn't speak too much to that specific process.
Okay. I remember many years ago, I was working with a company in Nashua, New Hampshire, and for a product I was designing, and they were making the mold for an injection molding process for a plastic part, and they were they made a graphite electrode, and they were doing the sinker thing. And I said, well, how long is it going to take to make this, to run this part? And this was machining the electrode. And they said, oh, it's going to take 24 hours to machine the electrode. Like, holy cow. I wouldn't put too much stock in that because I'm not sure how much I trusted the competence of those guys. But once they had the mold made, it was going like crazy. Do you see a lot of molds in your line of work?
At the shop I'm at, we used to do mold making, but it's moved more towards prototype aerospace work is what we're doing. So lower volume type work.
Pretty cool. Evils asks the question, are you ever concerned with swarf recovery / recycling?
So the swarf from the workpiece is pretty much a very fine dust that goes and collects in a filter in the back of the machine. And the spent wire actually, as it passes from the upper head, it passes through the part to the lower head, and then goes to the back of the machine and gets cut up and dumped into a trash bin. And then it's highly recyclable, so it's just brass.
So,
and I sent Spencer some.
Yeah. So this was cut up by the machine.
Yep.
That's pretty cool. Do you get
What's interesting is if you look at those pieces, you'll note that they're worn on 3 sides and not the 4th side. And
okay.
As the wire is pushing, it's only cutting on 3 sides of the electrode.
Okay. This is going under the microscope later. Obviously, I can't
it's
do
not
it right
going to
now.
show up on camera, but
yeah, it won't show up. But that's pretty slick. I think I get a little closer. I think it's neat that the machine is chopping it up. I didn't think of that. I had this picture of it going onto another spool and being spooled up, but why bother? VKTD says, I have found the most challenging part is trying to hold the parts for access. So holding the
that could definitely be true. Okay, yeah, go ahead.
No, go ahead. Let it rip.
Yeah, so work holding is, on the one hand, it's kind of easy because you don't have to hold your parts very tightly when you're cutting with a wire. It's a very low force cutting process, so you don't have to, try and resist your end mill or your drill pushing your parts around. However, you also want to have your cutting heads, or the upper and lower heads of the wire machine, as close to your part for ideal flushing. So you end up trying to grip things sideways often, and if you have features that extend above or below the top or bottom surface of your part, you deal with reduced flushing access, and that can make parts more challenging.
Tobbs asks, what's the material thickness where you're starting to get uncomfortable with both flushing the cut and wire vibration?
Let's see. I don't think I've run any parts that are so tall that we couldn't run them. The Cut Classic 3 has a pretty high Z height. I think we've done some 8 or 10 inch parts and had success in them holding tight tolerances.
Wow.
Oftentimes, getting the start hole in there can be tricky,
Yeah,
depending on if it will fit in the hole popper or if somebody else has to do it.
so
And
in the hole popper, there's very little force on the tool.
it works almost kind of like a Swiss machine. You have your chuck, which holds the part, it holds the electrode at the top. The electrode is maybe 10 inches long, the brass tube, and there's a ceramic guide near the bottom, and that's where the electrode protrudes and drops down into your part.
That is
So you
awesome.
have sort of a sliding headstock style of, grip the electrode and feed it forward through a ceramic contact
Mm-hmm.
and then down into your workpiece to be drilled.
Now I want an EDM machine. Of course, I have no room for an EDM machine, but you know who has room for an EDM machine? Ox Tools has room for an EDM machine, and hopefully
I've heard.
we will hear from him soon. I'm very excited about seeing him start to play with that. Lance, thank you very, very much for the goodies, and thank you very, very much for coming on and educating us. I appreciate it.
Yeah, thank you for having me, Spencer.
So we'll see you soon. Thanks, Lance. That was awesome. And of course, the items themselves are just too cool for school. So if you're in the neighborhood and you want to see it, stop by. Okay, we're starting to run out of time, and I owe some folks some information here. So when we opened, I was telling you guys about the anxiety that Unix Carbide had talking about magnets, and the fact when I said that aluminum was magnetic, he got really upset. So I wanted to give a quick brain dump. This is the dump and run. That's why it's at the end of the hour. I want to do a quick brain dump on magnetics and why we think magnetics are simple, but they're not simple. When we use there's a million consumer items that have magnets in it. This is a laser level that I have, right? I just grabbed this from the shop as an example of something that has magnets built into it. Of course, your simple we call it refrigerator magnets. Of course, my refrigerator now is stainless, so it doesn't work on that anymore. All of these standard magnets that we play with are in a class of magnetics called ferromagnets or ferromagnetism. And if it sounds like ferrous, you're not wrong. So there's a class of materials which end up being crystalline in nature, and they are very magnetic. And the magnetic behavior of a material comes from its outer electrons. So if you have unpaired electrons in a material, you have an electron running around, okay, in the orbit of your atom, and it has a spin. And if you think of if you ever made an electromagnet as a kid, you wound the wire around a nail and you turned on the battery and it became magnetic. You know that current running around in a circle is going to make a magnetic field coming out the top and the bottom of it. And it's called the right-hand rule if you're an electrical engineer, and it's the left-hand rule if you're a physicist. But so we know that a charge in motion is going to make an orthogonal magnetic field. So in ferromagnets, we're going to build a mental model for this in a second. But in ferromagnets, you have crystalline structures, and those crystalline structures, the whole domain is sort of aligned to point one way with respect to its magnetic field. If you can get all of those domains to kind of line up and point the same way, you end up having a permanent magnet. And if you have a bunch of those domains and they're not pointing the same way, but they are ferromagnetic, you might not have a magnet, but you have a magnetic material. So, we talk a lot about steels. In fact, when we're talking to Lance, right, we have different steels here. Well, the difference between steels is often in the crystalline structure, and very fine crystalline structure can get you some very very tough materials, and coarser structures might get you some hard but brittle materials, etc., etc. And that leads to heat treating, but it also affects the magnetic properties. So that whole class of materials and how they behave is under the heading of ferromagnetics. And let me give you a quick way to think about a ferromagnetic structure. So let's all picture a bunch of iron bars, okay? Well, let's back up a little bit. Let's walk up to a gate on a steel fence, okay? And it's got these rusty steel hinges. Have you ever opened up one of those doors or gates where the hinges are rusty and it's like, it makes a bunch of noise and then it stops, and then if you want to close it, you got to put a bunch of force, and then you got to overcome the friction of the rusty hinge, and you have to move it, okay? So we kind of know what a rusty hinge is. Now imagine a bunch of bar magnets, right? You go to the bar magnet supply, and you get a bunch of bar magnets, and we're going to put those on a rusty hinge right through the center, okay? And we're gonna nail those hinges to this big piece of plywood. So this is going to be a 2D mental model of this. So you have a bunch of bar magnets on rusty hinges on a piece of plywood. Now what I want you to do is I want you to go to the ends of all of these randomly oriented bar magnets, and we're gonna tape a rubber band to it, stretch the rubber band out a little bit, and tack that rubber band to the piece of plywood. So far this looks like a pretty good art installation to put on a wall somewhere. So this is a good model of a ferromagnetic material that, if they're all randomly oriented, it doesn't have an external magnetic field because they're all randomly oriented. Now we come along and we put a big coil of wire around it, and we start pumping amps through the coil of wire, and these magnets are going to tend to want to straighten out and follow the field being generated by the external coil. In order to do that, you have to overcome the rusty hinges. So for the moment, let's just decide we're going to put a gazillion amps through this wire wrapped around this piece of plywood holding our bar magnets with the rusty hinges and the rubber bands. And they all straighten out. And now we take the current away. Well, some of them are going to, the rubber bands are pulling hard enough. Some of them are going to kind of tend to go back. But because of the rusty hinges, on average, a bunch of them are going to stay pointing in the direction that we forced them into with the external force. You just created a permanent magnet. So now, because all of these bar magnets are all lined up, this plywood construct is going to act like one big magnet with an external magnetic field. So this is analogous to walking up to your the magnetic chuck on your grinder, putting a part on it, turning the magnet on. That magnet is going to not only attract the part, but it's going to rotate domains inside of your steel. And when you turn the magnet off, just stop the current. Those of you who have used or own magnetic chucks, you know that if you go to grab your part, yank it off the chuck, it's still stuck. So there's another setting called demagnetize. So what does it do? It's going to generate a current one way, and then the other way, except a little less, and then the other way, except a little less, and then the other way, except a little less. And what's going to happen is your bar magnets on their rusty hinges and rubber bands, you're going to leave some in some positions, and you're going to leave some in other positions. As that current goes down to zero, they're back to being random or back to being close to their original positions. That's demagnetization. And now you've got no external magnetic field. In the case of your grinder and your grinder chuck, now you reach over and you grab the part off the grinder chuck and the magnetic field is gone. That's ferromagnetism. And that's what we're used to. The act of having to push on that hinge, on the rusty hinge, until it starts moving, and then you have to do it the same the other way. You have to push on the hinge until it starts moving. That has a name. That's called hysteresis. In other words, it takes more energy to push it, to get it going, then and you have to use at least the same amount of energy coming back. So that excursion actually uses up energy, and that's hysteresis or hysteresis loss in magnetic materials. So this is pretty cool. We're starting to understand ferromagnets and how they work. And you could go search on the internet, and you'll find all sorts of electron microscope pictures showing domains, and you can kind of see how they're all kind of aligned, and that's all great. Along comes a piece of aluminum. And this is where Unix carbide is going to get kind of upset. But it turns out that behind ferromagnetism is another couple of kinds of magnetism. One of them is called paramagnetism, or we could say that a material is paramagnetic. And this one is actually pretty easy to understand, but it's a very, very weak force. So if you've got an atom, frequently you'll have these orbitals where you'll have pairs of electrons flying around, and their spins are opposite, the way of the world. So those electrons don't have an external magnetic field because there's one pointing one way and one pointing the other way. But if you have unpaired electrons, you have a population of electrons that do have a net external field. And this is the source of paramagnetism. So does aluminum have some of these unpaired electrons? And the answer is yes. So does that mean that you can observe a magnetic effect in aluminum? And the answer is yes. So years ago, I saw a demo of paramagnetism and its cousin diamagnetism, where and this was like a bar trick, right? You could take a material, make like a little barbell, and put it on a needle, on a cork, so it's nice and balanced, and then come approach it with a very strong magnet, and you can observe some attraction of materials that you don't expect to see any attraction of. And aluminum is one of them. And I didn't have time to prepare, like to build one of these things, but this is something we can build and we can test. Similarly, that's called paramagnetism. There's also something called diamagnetism. Now, what diamagnetism is sort of the opposite. This is where the material will tend to want to exclude a magnetic field and ends up making a force repelling it. And that's diamagnetism. So water is one of those materials. And one of the demos I saw years ago was 2 cherry tomatoes on a swizzle stick. Now, a swizzle stick is like one of these stirring sticks that you get at a bar. Don't ask me why I know this. And 1 cherry tomato on each side balanced on a needle in a cork. And you approach it with a stack of neodymium ridiculously strong magnets. and it moves the tomato. And it's not an accident. So you could have diamagnetism. The reason we never talk about this is because the force of paramagnetism, diamagnetism is so small, like really small compared to ferromagnetism, that we just don't see it. Carl says, why does this discussion remind me of demagnetizing CRT screens? Am I old? Yes. We're both old, Carl. But it's the same thing. The process that was used in CRTs to demagnetize stuff to get the CRT back to normal, okay, is exactly the demagnetization process that's in magnetic chucks on grinders. Okay, same thing. Josh says in recycling sorting, you can spin magnets on a drum and it will repel different materials based on the RPM. Yeah, it's pretty cool. Now there's another weird kind of magnetism called ferrimagnetism. Not ferro, but ferri with an I. And it's where you have a bunch of magnetic moments like we made in our example, and then you have a bunch of magnetic moments in the other direction for other reasons. Like maybe you have an alloy of something, and they can actually balance out. And you could have what's called a ferromagnetic material, where there's lots of magnetic action going on in the material, but there's nothing external. I have no experience with this type of material. I just wanted you to know it exists. And there's one other behavior I want to point out, which is the eddy current behavior. Now, this is different, and this has nothing to do with ferromagnetics or paramagnetics or diamagnetics. Eddy currents are when any conductor moves through a magnetic field. And for example, the magnetic vein on my scale that I was using downstairs to measure the desiccant packets the magnetic vein moves between two strong magnets, and it damps the motion. And it repels motion. So if there's no motion, there's no impact from eddy currents, but it will cause things to stop moving or slow down. So you have to be careful if you're going to demonstrate or seek to demonstrate paramagnetism and diamagnetism. You got to be careful that you don't confuse it with eddy currents. Just so you know. So there's a couple of terms that I'm going to leave you with. One of them is permeability. Permeability is the ability of a material to concentrate magnetic fields. So, for example, a piece of mild steel might have a permeability of 100. That means you could squeeze 100 times more magnetic field lines in a piece of steel than you can in air. So we say that air has a relative permeability of 1. And that piece of steel may have a relative permeability of, 100. So here's a material, if you're watching the video, this little ribbon of metal. This is called, it's a trade name. It's called Met Glass, M-E-T, Mike Echo Tango, Met Glass. It's also known as amorphous, an amorphous alloy. It's a highly magnetic nickel steel alloy, or nickel iron alloy. And Met Glass is very flexible, very strong. And it's, those tags on products at Home Depot so that you don't steal it and walk out the door. Frequently, they'll have a little piece of Met Glass in them. And that Met Glass, I'm not going to get into how the tags work. That's a little complicated. But this material here is made by spraying the alloy in its molten state onto a drum, the drum being cooled by liquid nitrogen, and it freezes very quickly, and it makes an amorphous alloy. That means it doesn't have crystals. So, or another way to say it is that the crystalline unit is absolutely tiny compared to other alloys. This stuff has a permeability of 1,000,000. Okay? Just to give you an idea. Now, water has a permeability lower than 1. That is the diamagnetism. And aluminum has a permeability greater than 1, but not much. So there you go. We talked about permeability. The other thing is coercivity. Remember we talked about our magnets on our rusty hinges? Okay. The ability to coerce the magnets on the rusty hinges into the position you want to leave them in is called coercivity. So there are some materials that are magnetic, but you can't make them permanent magnets. And there are some materials that are not really too magnetic, but you can make them, permanent magnets. Snatchy Poo, Kyle, says, kind of curious how effective met glass would be as a stator/rotor motor material. Fine question. Motors have stacked magnetic plates to control magnetic field. This stuff comes only in this form factor, so you'd have to wrap it, which, that's done. I will leave this as an exercise for the student. It's pretty cool stuff. Amorphous metal alloy, okay, is what met glass is. Look it up. Here's how you spell it for you guys on the video. That's the trademark. Why do I know about met glass? A story for another day. So there you go. Lots of ways to acknowledge that there are magnets everywhere, and even Unix Carbide doesn't know about them. Oh, well, guys, I think we did it. We have hit everything, and hopefully we survived YouTube today. Feedback on the YouTube behavior live and also, recorded is welcome. I'm going to wish you guys a great Sunday. We went a little bit over, but we were having a lot of fun. I want to say thanks to Lance K, both for the goodies. Carl asks a great question. I'm going to answer Carl's question because I have to. It's Carl. Carl says, so is met glass a better shield than mu metal? Carl, the answer is yes. Absolutely yes. I'll just leave it at that. You could take this stuff and you could take this stuff and weave it into a material and use it for low frequency magnetic shielding, and it works great. Look it up. It's pretty cool. All right, guys, we'll be back next week. I don't think there's any reason we shouldn't. And if you guys have any topics you want to cover, I will remind you our problem solving exercise with Tom Lipton and Robin Renzetti. The problem process is still live. We're still looking for more inputs. If you have an interesting problem you want to drop at the feet of these guys and watch them solve it live, go to pfg.gg/links, and real close to the top of the page is a big honking red button and a portrait of those gentlemen. Hit the button. It'll bring you to a Google page, and you'll be able to, or Google form it's called, and you will be able to input your idea. Okay. And we're still accepting entries. We want about 5 times more than we already have. If you need some flat stones, head over to PFGstones.com and pick yourself up some stones. We'd just have a batch of 4-inchers ready to finish up, and those will be heading out the door. You know who you are. Also, don't forget about molybdenum. If you use diamond wheels in your work, and you want to try molybdenum truing, or if you already know about molybdenum truing, head over to pfg.gg/moly. We got a spike of moly orders this week, so you could go check that out. Meanwhile, get flat and stay flat, and we'll see you guys next week. Take care.